Hi, good evening, everyone. So Miss He and Miss Dreckles decided to actually just go over every single exit ticket in Unit 3. I know it's very hard for us to just post the work in Google Classroom and wasn't explaining too much, or we got 8 lessons, and then our flex day on Friday wasn't actually like long enough for us to cover every single lesson. I know in Unit 3 is gonna be a very upbeat, like fast-paced lessons for this 8 lessons in unit 3. So I decided to just do a little video to introduce every single exit ticket in unit 3. So that is going to be a super fast recap, and also will be actually having extra time for me to slow down to explain things bit by bit. Hopefully this is going to be helpful. Hopefully this is going to be helping you guys. Okay, so let's take a look at Unit 3, Lesson 1. So in this exit ticket, and the question says the graph below represent the reduction in percent coverage of a mold on a food after application of certain chemical. So that means it's actually showing by reducing based on what we see right here. Now we know that in this trend, let me go ahead and use the color. So based on this trend, we actually see a decreasing trend, like just by observing. We know that first, this is going to be a decay. Now, as we observe as a decay, that means whatever's inside the parentheses, that means like in our growth rate, the A, B, and T, right? So this B is actually going to be represented by a number that's between 0 and 1. Why was that? It's because we don't talk about negative things, and then when we equal to 0, that whole thing will become 0. So we can actually be equal to 0 or negative. And as we're talking about decay, this thing have to be in between 0 and 1. So we need to have a fraction. Just by doing this, we know that this is out, and this is out. The only thing that happening is going to be the 1/2 and the 1/2. Okay, so since every single body is actually having an x power, so I don't really care about which one do I choose for the exponent, right? So because they all satisfy with the x power. Now the next thing that I need to take a look at, okay, so based on our equation ABT, I know that there's supposed to be a place talking about A, which is our initial. Now based on I observed, some number in our initial have to be above 60. So the initial have to be greater than 60. So, okay, I got 64 and 64. Great. But the thing is, observe our equation. I actually have a times right here rather than a plus. So I know that definitely our answer is A rather than any other things. Now, again, as a recap, let me go down a little bit right here. So as a recap, the A and B and T is the one that we use in every single situation without the word exponent. With the word exponent, without the word continuous, without the word compound. Now in here we have P0, 1 plus R over N, and then NT. This is the one that used in bank most likely. Every single time we talk about bank, use this one. And then we here also can actually be using the English word compound. Now, it doesn't matter compound quarterly, compound semi-annually, compound daily, compound whatever. The N actually represents like how much is the time that you're getting within 1 year. Oh, if it's 365 days, the N should be 365. And then the N should be happening right here also. Okay, so the last one is going to be the one that we don't talk about much. It's going to be our E. So the one that is within for the one that we mentioned about E is actually called compound continuously. When we have the word compound continuously, we need to talk about all of those like being paid every single millisecond. So this is why in here we have to talk about the one that ends with the E. Okay, so that one was the one that wasn't actually showing a much, but I'll actually give you the formula if it ever happened. If it ever happened. Okay, so let's move on to question number 2. Now in here, we actually have a table shows how fast a certain type of bacteria multiples. Again, if it's talk about bacteria growth, any of the normal things, we just might be thinking about this one, which is our normal growth rate. But let's finish reading the whole thing first. So in here, identify the y-intercept. That means most likely our y-intercept is going to be our initial, and the growth factor, which is our rate actually. Okay, So we have two things, initial and our rate. Okay, keep reading. In order to write a function that can be used to determine the number of bacteria after X number of hours. So that means our unit for T is actually in hours. So T unit. Unit is 4 hours. And then use the function to determine the number after 15 hours. So that means we're actually looking for the number 15 right here and try to figure out what's inside this box. Now, first thing, we have to find our relationship. So let's take a look at our equation. Right here, we know that we did not mention the word compound. We did not mention the word continuously. So that means our normal equation is going to be like this, ABT. Sorry, by the way, f of x though. F of x equal to ABT. Now here, y-intercept, they said identify the y-intercept. That means literally asking you to look for the word 8. A in here, y-intercept 0, 1. Okay, so that means I start with 1. Now the times still need to be copied, just the times. Now B, how to actually analyze and find B? All we gotta do is check for the consistency and check for the step, right? Here I times 2. Here I also times 2. Here I times 2. And here checks out, here checks out, and here checks out, and here also checks out. So that means our B is just what? Doubling, right? That means doubling just for B is 2. And right here, T is just T because I still have a function. Function unknown is not going to change much. It's going to be leaving like a T or an X. Okay, in here, I need to plug in the number 15. I know 1 times everything is just whatever number that I use for, so just 2T. Now here, I need to plug in T for 15, so I need to look for 2 to the 15 power. After you punch in a calculator, you got 32768. Now I know this is going to be a whole number and I still have to give it a unit. Oh, count of bacteria. So you can say the word bacteria. Just like that. Okay, hopefully this is going to be helpful for unit 1. Unit 3, lesson 1 exit ticket. So let's take a look at lesson 2. Now in here, lesson 2, we actually did a recap on the last Friday, and also we did it on the exact day when we're teaching lesson 2. So let's take a look at this one. Okay, our graph looking like this, like a very normal airplane taking off shape. So we know that this is definitely going to be a exponential growth. Okay, so it asks where was it increasing? I was actually explaining very clear on the Friday that when we do a recap on this is every single thing that, and when you have an asymptote, look at this one. My asymptote means that your number is getting close, 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 but you never touch it, right? So as an extension, and then on the other side, it just go up to infinity and beyond, just like Buzz Lightyear, right? So in here, I get super close, and on the other side, I just extend it to go up forever. So where does increasing? How to actually talk about increasing is like I put my pen right here. Pretend I have my pen right here. As I move along to the right side, oh, actually my value is going up and up and up. So it doesn't matter where I start, is because if I go to the left, that means if I keep decreasing, I still decreasing. That means I wasn't actually going up, just like a happy face, right? So in here, I am actually having an increasing in every single place. This is the one of the most important thing about exponential growth. So exponential growth means growth everywhere. Growth everywhere. Now, how do we actually define the word everywhere? That means x included every single real number, or we can call from the negative infinity to positive infinity with the parentheses, or negative infinity, less than 0x, and less than positive infinity. All these three are actually meaning the same thing, which is x included in every single real number. And that is actually set. So that's what I forgot. I actually need to open the bracket for it though. That was a set. And here, what if I'm actually giving you a airplane landing style? Airplane landing. And here I'm actually having an exponential decay. And that means in here is actually a decay everywhere. That means no matter where I land, no matter like what area that I'm talking about, this chunk, or maybe I'm actually talking about this chunk, no matter what chunk am I talking about, this is always going to be decay everywhere. So when the question asks you, oh, exponential decay, where does it decay? Where does it actually decreasing? Oh, you gotta say everywhere. And then when you're asking for about exponential growth, just like this normal graph, where is it increasing? Oh, everywhere. So again, when we were talking about where, you have to talk about an interval. When there's an interval, you gotta talk about a domain. Okay, domain of x. Okay, describe the end behavior. After my explanation on last Friday, I still have a lot of friends who are actually thinking about, oh, I just need to talk about one end. But the thing is, no matter what graph it is, every single graph on Earth is definitely going to have two different ends. So you have to talk about two ends. Most important thing is two ends. They always have two ends, two ends, two ends. Now on the left side, you can talk about left end goes to and then right end goes to. So that is definitely going to be the two things that you got to start with. Misspelled, sorry. Right end goes to. Okay, so left end goes to where? As I told you, exponential growth and exponential decay always have an asymptote. And if that is not move around, so even though that this is going to be an enlargement when I have a coefficient of 3, that means I'm not moving up or down. So that means my asymptote wasn't changing at all. So that means my asymptote is due at 0. Let me change the color and label that y equal to 0. Y equal to 0, that's my asymptote. Okay, so when I have my asymptote, I am not touching it. Again, we don't touch it, we don't go past it. That's what the asymptote means, right? We don't touch it, we don't go past it. So that means I know that this trend is going so close, so close, so close, but actually not touching it. So my left end actually goes to 0. Goes to 0. My right end is, look at this, it's actually going all the way up to the sky. So that means my right end is actually going to positive infinity. And that's going to be the only correct answer right here, and the only answer that I'm going to accept. Okay, let's take a look at what about exponential decay. Again, same example, and I will say left end goes to positive infinity because it'll go up forever. Then right end goes to 0 because my right end is going to go close to my asymptote, which is y equals 0. So close, so close, so close, but it never touches it. So this is why my right end approach 0 and left end approach positive infinity. It would be the best for you to actually use the word approach. So doesn't actually goes to, approach also work fine. P-P-R-O-A-C-H. Approach. Okay? Oh, approaches. Okay. What should it be? ES. Yep, should be ES. Approaches. Okay. So again, whatever that you are going so close to but not touching, that is going to be your end behavior goes to. Again, every single graph on Earth have two end behavior. One on the left, one on the right. Okay? Okay, next one says the domain and range of this -1. So this is our original graph, and when it -1, that means my graph actually moved down a little bit. So this is my original graph, and then my -1 graph is going to be something looking like this. That means that it's going to be not touching, but it goes so close to the -1. Y equal to -1. Domain. Domain for every single exponential growth or exponential decay is always going to be the same. Always, always, always. Which is x inside every single real number. Open a set for it. Now, range is always going to be starting from the asymptote to either one the other end. So if my left end start at asymptote, right end goes to infinity, then you should write start at asymptote, go to infinity. Oh, actually, positive infinity with a parentheses. Again, why do I use parentheses? Is because that is my asymptote. I'm not gonna touch it. Okay. Again, using our example for exponential decay. So, for example, actually moved down a little bit. That's perfectly fine. I moved down to -1. But now I start from negative infinity. That means on this side, that's negative infinity. When I'm talking about range, I'm actually going from positive infinity. And in here, I'm going to -1. So that means I'm still going to use -1 going to positive infinity. But if I'm actually moving that to the other way, for example, something like this, right? Then when I talk about range, this is actually going approach negative infinity because it goes down, right? And the other side, and it goes up, and then the biggest number I can get is very close to 0. So that means I'm going to have negative infinity to 0. That is going to be a range for this kind of graph. Again, Reading the range, that means I'm reading from bottom to top. Doesn't matter, always from bottom to top. This is how you read the range. Again, read from bottom to top. And then for domain, left to right. Always left to right. That is your domain. So again, domain, read from left to right. Always start from smallest to biggest. Range, also the same thing. Read from bottom to top. Why? Because it's smallest to biggest. Okay, very last one. And the only thing that I add from the original is just the negative sign. Again, negative sign in the front means flip upside down. Upside down. If, no, E. Okay, if, geez, okay, sorry. And then if I actually add a negative sign in front of the X, so it's going to be 3 and then 2 negative X power, that means flip left, right. That means flip according to the y-axis, or you can call it like a single lady dance. They have to flip on the left side right or right side left. And that means flip upside down. Okay, and let me just go back. Let me erase all of this breaker back and erase all this extension and mirror it upside down. So actually, I'm actually having here, and it actually go down that way. Okay, that's how you actually draw this graph.